Today we're going to take a look at a technique for finding an original function called separation of variables. Okay. Separation of variables is, I usually think of it as kind of like undoing implicit differentiation. So it's kind of like implicit anti-differentiation. We're kind of working backward. We have a differential given to us and we want to find the original function, usually in terms of y. And so we have to separate all of our terms with a y on one side with the dy and all of our terms with an x on the other side with a dx, and then we take an integral of both sides. Okay, so let's take a look at what I'm talking about. We'll start with a very basic, easy one. Let's say we are given the differential dy dx equals 2x over y. And we want to find what's called the general solution. So we'll still have a C value. Okay, we don't have an initial condition. We can't find the C value. So we're going to find the general solution. We want to get the terms with a y with dy. So we're going to have to multiply over by y. And then we're going to move the dx over by multiplying by dx so that the dx is with the x terms. Okay, so now we have y dy equals 2x dx. So let's take the integral of both sides. That would give us y squared over 2 equals x squared plus c. Okay. At this point, I would actually leave my equation as is and kind of wait, because if we need it for something else, then we will have to find our initial condition if they gave us one and find our c value. For this one, this is a general solution. Y squared over 2 equals x squared plus c. That would be a general solution for this function. Okay. Let's take a look at one that might be a little bit more work. Let's say we have, do some trig as well. Let's say we have dy dx equals x plus sine of x over 3y squared. And we want the general solution solved for y. Okay, so we'll take it a step further. But we're going to start the same way. We need to separate and then integrate. So if we move 3y squared over with the dy, multiply by dx, and then we have x plus sine of x dx. Now we have these separated, so we can take the integrals. Integral of 3y squared dy is going to be y cubed. Integral of x plus sine of x dx gives us x squared over 2. Oops, almost put a plus there. Oh dear. X squared over 2 minus cosine of x plus c. Now, we said solved for y, so we do want to solve for y. We have y cubed, so we need to take the cube root. So the cube root of x squared over 2 minus cosine of x plus c. And then we would leave this as is because we don't know the c value. Okay, so that's the most we could do for that one. All right, let's try another one. This is one that looks very easy to begin with, but ends up being a little bit more complicated. Let's say we have dy dx equals 4y. Okay, well, we don't even have an x in this equation. Okay, we need to move the y over, so we need to divide by y. So we could say 1 over y dy equals 4, and then multiply by dx, put it on this side, so 4 dx. Now we've separated, and we can take our integrals. Maybe if my pen will decide to cooperate. So if we take our integrals, integral of 1 over y dy is natural log of absolute value of y. Integral of 4 dx would be 4x plus c. Now, how do we get rid of a natural log? Okay, in order to get rid of a natural log, we have to exponentiate the functions. Let's use e. Okay, e to the natural log of y cancels, right? And we have y. And now we have e to the 4x plus c. Now, there's something I want you guys to think about, because when we have functions like this, say this was a multiple choice question and they asked you to find the general solution, they may not leave their answer choice as e to the 4x plus c. Okay, so what I want you to think about is, remember exponent rules. Remember exponent rules. If we have e to the a power times e to the b power, that gives us e to the a plus b. Whoops, not a. Oh, goodness. E to the a plus b power, right? We can add those exponents. So we could also break those apart. If we start out with e to the a plus b, we could change that to be e to the a times e to the b. Think about what we have here. We have e to the 4x plus c. We could say that that is equivalent to e to the 4x losing my pen here. E to the 4x times e to the c. Okay, that's just using our basic exponent rules. Okay, so if we use that, now e to the c is just a constant, isn't it? Okay, so e to the c is just a number. What if we call e to the c a k value? Then we could rewrite this as e to the 4x times e to the c. If we say e to the c is k, then that would be k e to the 4x. Okay, guys, the only reason I mention that is so you understand where that solution could come from. We could have either of these in a multiple choice situation. Okay, so just keep that in mind. If you're solving, you have an initial condition, then you're going to have to use your initial condition to find the c value, or you could use the initial condition to find the k value, depending on where you wanted to solve. It doesn't matter. It just depends on what it ends up being. If you end up solving for c, a lot of times you'll get a natural log and you'll have to pull it out front anyway. So sometimes it's a lot easier to just rewrite it as k e to the 4x. That becomes a little bit more important later on when we look at some other types of equations as well. But I wanted to go through why that works so that you know. All right, let's try one with an initial condition. Okay, so let's say that we have dy dx equals xy. Oops, not xy, excuse me. Dy dx equals 1 over xy, and we have an initial condition that y of 1 equals negative 4. All right, so let's go through. Let's start solving just like we normally have. We want to separate and integrate. We need to multiply by y to get it on the other side with the dy, multiply by dx, so we'd have 1 over x times dx. Now we have our variables separated, so we can take these integrals on both sides. Okay, integral of y dy, y squared over 2. Integral of 1 over x dx is natural log of absolute value of x plus c. So now, if we go through and we solve for c, let's just go ahead and solve for c. That's what I usually try to do so that you don't get too complicated. Where are you multiplying things? Where are you dividing things? Go ahead and solve for c. So y in this case is negative 4. Okay, so we have negative 4 squared over 2 equals natural log of absolute value of x. X is 1, so natural log of 1 plus c. Natural log of 1 is 0, right? So that's gone. And then we have negative 4 squared over 2. Negative 4 squared, 16 over 2 is 8 is our c value. Now, let's rewrite. We had y squared over 2 equals natural log of x, absolute value of x, plus 8. Let's get this in terms of y. So we got to multiply by 2. Okay, now we need to take the square root. But I want you to think about your initial condition. Notice that our initial condition was y1 equals -4. So in order to get that -4, if we're taking a square root, we got to put a negative on the outside in order to get that negative answer. So y equals the negative square root of, I've lost my function here, negative square root of 2, oh boy, of 2 natural log of x plus 16. Okay, so notice that we had to take the negative square root. Otherwise, we're not going to get the right answer with our initial condition, are we? Okay. Anytime you have a square root, you always want to go back to that initial condition, take a look at what sign it was. That tells you what sign your square root would be. Okay. So for this one, we needed a negative square root. If it had been y of 1 equals +4, we would have had the same c value, but we would have had the positive square root instead of the negative square root. All right, let's do one more with an initial condition. Let's say we have, excuse me, y dy dx equals cosine of x, and we know that y of 0 equals 3. Okay, we want to work backward and then use our initial condition to find the c value. The only thing that we need to move in order to separate is move the dx over with cosine of x. So y dy equals cosine of x dx. Let's take the integrals. Okay. Integral of y dy, y squared over 2, equals integral of cosine of x would be sine of x plus c. Oh, also something I should probably note, I'm only putting a plus c on the side with the x because we don't need more than one c value. Because even if when we took the integral of the y term and we had a c value, we could just subtract it over to the other side or add it over depending on which sign it was. So we only need one c value. So conventionally, we just put it with the x term because that's easier and because we usually want to get this in terms of y equals anyway, just as an FYI. Okay, let's plug in our initial condition. 3 squared over 2 equals sine of 0 plus c. Okay, well, sine of 0 is 0. That's gone. 3 squared over 2 is 9 over 2. So that's our c value. So we now know that the c is 9 over 2. If I could write, there we go. So now we just want to rewrite our equation, and we're going to solve for y again. So we have y squared over 2 equals sine of x plus 9 over 2. Oh my word. There we go. Okay, so let's multiply by 2. So y squared equals sine of x plus, whoops. What is going on here? Okay, so y squared equals 2 sine of x plus 9. If we take this square root, now notice our initial condition, y of 0 was positive 3, so we want positive square root. So y equals the positive square root of 2 sine of x plus 9. And that would be our equation that would work for this differential and the initial condition. This is called the particular solution. We've done that before with integrals. We just had not done that before with separation of variables. So the big thing for these guys, you have to use separation of variables. We cannot take an integral of a function that has both an x and a y. So we have to separate in order to be able to take the integral. A lot of times these show up on free response questions, and you get no points if you don't try separation of variables. So make sure that you are separating these functions because you cannot actually take the integrals without separating the variables.